And hello YouTube, welcome to this video where I am doing like my Rust learning journal, or rather, yeah, Rust simulation learning journal. So the last time I was talking a little bit about, yeah, just getting the basics of cargo setup and cargo watch. So today I want to do something a little bit more interesting, right? Instead of just loading you with more and more information about how to do programming language, let's jump straight into application. And then we'll just pick up, I'll just introduce stuff that makes our life easier along the way. Okay, so it's probably easier, let's say, for us to learn like that. Okay, most of the time, you'll probably be doing real world applications like that. And yeah, you want to see some real world applications. If not, what's the point of learning? Yeah. So today's real world application is ODEs, ordinary differential equations. Specifically, we'll be looking at a very common problem called Newton's law of cooling. So Newton's law of cooling is basically when you have, let's say, a body, it could be a stone, it could be a sphere, it's hot. Maybe it's about 1000 degrees C. Okay, just giving you an example. Do pardon the handwriting and all. I am not being paid for any of this. I'm not doing this for money. Just doing this out of a hobby. So do pardon me. I'm not professional in doing this. Okay, so it's a 1000 degrees sphere. This thing is losing heat to air maybe about 25 degrees C. Okay, 25 degrees C. Okay, I'm using my mouse to write again, so do pardon it. Hope it's somewhat legible. Maybe I'll do it a bit nicer. Okay, so 25 degrees C. Okay, 25 degrees C. So over time, this stone or pebble or hot, I don't know, ball of steel or something, at 1000 degrees C, it may be probably melted. Maybe let me reduce it to 400. Then it's a solid. To 400 degrees C. Yeah, 400 degrees sphere, it will lose heat over time. Okay, what is the equation that quantifies that heat loss? Okay, what's the equation that quantifies that heat loss? The equation here is Newton's law of cooling. You may have seen this before. It's very common. Q equals to HA. HA is the constant of the heat loss. You actually study heat transfer. H is the heat transfer coefficient. A is the surface area. Q is actually the heat lost per unit time. Okay, so what's the heat heat rate? What's the rate of heat loss? So it's actually, well, when you start out, it's 400 minus 25, but the ball temperature is going to slowly drop over time. So it's the T of the solid. Okay, T of the, maybe I'll use this, T of the solid. Right, yeah, T of solid. Okay, minus, right, minus T of air. Yeah, I'm going to use this, air. Okay, and then I'll close bracket. Okay, this is more or less Newton's law of cooling. Okay, so the rate of heat loss is equal to T solid minus T air. Okay, so how do you then compute the temperature of this ball over time? Okay, so I'm going to make a very simplifying assumption, and I'll assume that the ball has some uniform temperature. There are certain conditions where this can hold true, but this is one of the most simple simplifying assumptions. So the ball temperature here, we assume it is uniform and constant. We call this a lumped heat capacitance. And the rate of change of this, okay, the rate of change of this ball temperature is described by MCP dt by the time. So this is the temperature of the solid. Temperature of the solid here. Okay, let me fast forward this bit so that you don't have to see this. Okay, so the rate of heat, the rate of yeah, the energy change of this ball or this solid per unit time is measured by this equation. Now, of course, there will be a minus sign right here. If okay, I'm going jumping a bit too far ahead. So the rate of change of energy for this ball is equals to the rate of change of heat loss. If there's no other heat source or anything, these two terms here and here will equate. There will of course be a minus sign right here. Yeah, but that is going to be our starting point. This is the classic Newton's law of cooling. And if you're worried that, we'll keep having very poor fonts, don't worry. Here we are. We have a much nicer font. This is types or tipst. I'm not sure how to pronounce it properly, but I'll just call it typest. Okay. If you think it is tipst, I think you can leave a comment there. I think the original authors are supposed to, they said they might want to name it like the tips, TYPST. Supposed to it's supposed to rhyme with hipster or something. But regardless, I'm going to use that program. It's written in Rust and it provides somewhat of an easier replacement compared to LaTeX. So okay, here's what we have discussed just now. MCP dt equals to minus HAT minus T surroundings, where T here is here of course equals to T solid. Okay, if you want to learn how to use tips or types, just let me know in the comments. Of course, you can search your own video tutorials online, but for now, yeah, leave it in the comments. If there are no tutorials online, well, I'll see if I have the time to do it. Tips tutorial or types tutorial. I like calling it types. Okay, so this is the equation we're supposed to solve. All right. So how are we supposed to compute this ODE using something like Rust? Okay. What we will normally do is to approximate this derivative using a finite difference equation. Usually that will entail T solid at maybe, let's see, T plus delta. Oh, let's miss. Oh yeah, I just forgot how to write Greek letters in types. I'm more used to LaTeX. I haven't been using types in a long time, but it appears I can just get rid of this backslash. You use row, delta, etc., etc. You should be able to get the Greek letters. So I'm just gonna do it like so. Yeah. RD. Okay. There you go. T plus delta T. Okay, minus, I'll paste this whole thing here. Don't mind if I use Vim for the time being, because anyway, I'm not going to teach types or tips. So yeah, I'm not going to teach types or tips. The whole idea is to focus on Rust. Okay, so here's what we are supposed to do. This is the Euler method. Okay, we say MCP T solid at the next time step minus T solid at the present time step is equals to minus HA T solid minus T surroundings. Now T surroundings is a constant. We can assume it's a constant. And this T solid, well, we have two choices what temperature we can apply. Right, if we say this T solid here is the temperature at the next time step, then we'll have what we call an implicit time stepping method. So let's take a look. Implicit time stepping or implicit Euler method. Okay. I'll put this over here as, all right. Oops. I'll just highlight this and I'll paste it here. This is what the implicit method is supposed to look like. And of course, if you want the explicit method, then that will be the previous time step. Okay, explicit and D2. Okay. Okay, so this is what the explicit time stepping method is going to be like. Now, of course, what you're supposed to do now is to do some factorization. Okay, so let me do the implicit method. Let's do, let me make the font size smaller. Explicit. Let's do implicit method. Should not be a problem. It's a very simple problem here. Okay, what we're supposed to do is we're supposed to combine both of these. All right, I'm going to bring that HA to the side. Okay, so this is going to be HA. I'll paste it here. I'll paste it here. Change this to a plus. Cancel this out. I'm going to bring it over to this side. Plus. Let's see whether it turns out right. Oh, right. That's an error. Ooh, shoots. Okay, that was not intended. T solid T plus delta T. Okay, this should go here. Right, so the HAT solid at T plus delta T, I'll move it to the left hand side. There'll be no more minus. This fella here, I'll leave it on the right hand side. It will be a plus. Okay, so that's what we need to do. And what next? We'll just move MCP T solid over delta T to the right hand side. Okay. So plus MCP CP, okay, T solid divided by delta T. Okay, I'm gonna copy this, paste it here, and I'm gonna delete this term. Okay. So yep, it looks okay. T solid T plus delta T is here. The solid temperature at the last time step, it will be all moved to the right hand side. Next thing I'll do is to factorize out this T solid, because we are getting quite close to what our expression should look like. So I'm going to factorize out this T solid. Okay, we'll have brackets here. Factorize out the other T solid. Okay, and I'll move MCP to the top of the fraction. Okay, so I'll move MCP to the top of the fraction. So this is what the thing should look like. Okay, move this thing to the right hand side, and basically we will have a scheme to always get our next time step temperature. So I'm going to put this here. Put this here. I'll put a fraction 1 divided by whatever is inside here. Yank, paste. I'm pretty sure I forgot something. Okay. I don't think I need the brackets. Do I need the brackets? Oh yeah, I do need the brackets. I'll leave the brackets here. Yeah, I'll leave the brackets here. Okay, so this is what this should look like. I don't want too many square brackets though. I'll maybe use curly braces. Oh. Yes, that looks a little bit nicer. Okay, so this is what our equation should look like. Assuming that there are no careless mistakes, Okay, the T solid at the next time step using this implicit scheme, okay, is 1 over MCP divided by delta T plus HA. So this is the heat transfer coefficient times area. Is the thermal conductance, in other words. Then HA T surroundings plus MCP T solid over delta T. Okay, so this T solid will be at the last time step. Okay, so right, we have a way for ourselves to compute this ordinary differential equation, solve it numerically using the implicit Euler method. Now, the trick is to do all of this now in Rust. Okay, so what do we need to do in Rust to get this done? So I'm just going to minimize this, and let's open VS Code. Okay, let's open VS Code right here. Right. Okay, so this is the Newton's law of cooling, and what I want to do is maybe let's you can see that there's so many there are so many variables going on here. Maybe what I want to do is I want to write all of this in a new file. Okay, let's write all of this in a new file. So let's say I have a file, I want to make a new file. Okay, I'm going to use VS Code now. Let's say I want to make a new file. Let's see how much time I'm going. Okay, so let's do making a new file. I'll call this Newton's law of cooling.rs. So this is the Rust file that just describes Newton's law of cooling. Right, and I want to name a function here, implicit Euler method. Okay, so this is the name of the function. Remember, the function is just a block of code that is just a block of text or that describes some code that we want to run. Okay, this is a function here. Okay, now what do we want to do? We want to run the function from the main file. How do we do that? Okay, so you see this thing, this is in a different file. If I try to run this implicit Euler method right here, we'll not be able to. So let me just demonstrate that we are not able to do that. Implicit Euler method, and let's try. We will get an error. Okay, it says this function is not found in this scope. Okay, there are a number of things that we need to do. Okay, there are a number of things that we need to do. You see, we have actually pretty much copied, well, we have the same syntax here, right? We have function and then the function name, two open and close brackets, and then two curly braces right here, right? So this block of text, this function here is also the same. Two curly braces and two normal brackets and one function right here. Why isn't it being detected here? Because Rust doesn't know, or Cargo doesn't know that you want to consider this function yet, because this function is in a different file called Newton's law of cooling. To actually access this function, you need to do something like this. Okay, this is very similar to import for Python or whatever, but just for Rust, we use the term mod, M-O-D, mod Newton's law of cooling, Newton's law of cooling. Okay, and now we see that the error is different. Okay, it says Newton's law of cooling implicit Euler method exists but is inaccessible. Okay, so what does that mean? It means that well, usually even if you declare functions over here, what Rust by default does is that, you know, the functions are not exported. So you'll see this thing called not accessible right here. Okay, so let me slow down and explain before I move on. Okay, so okay, never mind. Maybe I'll just demonstrate. Okay, the way to fix this kind of accessibility problems, okay, the easiest one-size-fits-all so-called solution, but it's not truly a one-size-fits-all. There are problems with that, but this early on, you don't really have to think that much. Okay, this what you need to do is to change this to a public function. Okay, a public function. Okay, you need to call this make this function public. Okay, And then now it says here, the error message here is cannot find function implicit Euler method in this code. Consider importing the function create Newton's law of cooling implicit Euler method. Okay, so well, we can do what the compiler just suggests. Use Newton's law of cooling or create Newton's law of cooling and implicit Euler method. Do this and you will be fine. Okay, so what was going on here? All right. Normally, we don't have to make functions public, okay? Unless they are of different files. Okay, functions by default, they can only be used within the same file. So you see this main.rs here. Main.rs here has two functions. One is the main function which we will always run, and then the last video we actually made a function called experiment1. Now because these two functions are in the same file, main.rs, okay, or they will be accessible within each other. What do I mean? Okay, if main is in the same file as experiment1, main will for sure know that experiment1 exists, okay, because they are in the same file. Now once these functions are in different files, main doesn't know that implicit Euler method exists. Okay, that's why we need to do this. It does not know the implicit Euler method exists. It does not even know that the Newton's law of cooling exists. That's why we need the mod file. Okay, so if you want to delete the mod file, you will see that it says we cannot find the Newton's law of cooling just now. So to make this file aware of, make the file in main aware of this file called Newton's law of cooling, we use the mod keyword. Okay, the mod keyword. Now, so the mod keyword makes this main file aware that Newton's law of cooling.rs exists. The second thing we need to do is to so-called import the function. To import the function, we use this use keyword. Okay, use create Newton's law of cooling implicit Euler method. Okay, so create is, well, this whole package, we call it a create. Okay, under this create has this file Newton's law of cooling, and under Newton's law of cooling there's an implicit Euler method, which is this function right here. Now the function right here by default, because it is in a different file, it is locked away. So functions within the same file, they share information with each other, but once it's between files, they will stop sharing the information with each other. Okay, by default, these functions within the same file, they are private, what we call private, meaning to say if they are within the same file, you share the functions, the functions know that each other exists, the functions know the existence of each other. Excuse me. So the functions know the existence of each other, but once it's in a different file, they not only have to be told that the other function exists, okay, these functions also need to be exported. They have to be marked for exporting or marked for export. Okay, to mark them for export, you use this pub keyword. Pub actually stands for public. So mainly when you make the function public, okay, when you make the function public, you will be able to call it from another file. Okay, that's the whole idea of this public-private thing. Okay, you will see this a lot of times in Rust, especially when you start including stuff from different files. Okay, so that's the first thing. Okay, this is something you'll probably run into less often in MATLAB. And I guess my time is already run out. It's already 25 minutes and I don't want to drag the video too long. But okay, so we have actually just discussed the problem we want to solve, and then I'm trying to introduce you some tools that you can use to solve in Rust. Okay, so for now I'm going to stop the video. So I'll see you next time. Okay, bye-bye.